So Tower of Hanoi is a puzzle which was invented by the French mathematician Lucas in 1883. It's a classical example of recursion. Recursion we use in a number of problems, but Tower of Hanoi is a classical problem in which recursion is used. So what is the problem? The problem is there are three number of pegs. So these are known as pegs: source peg, auxiliary peg, and destination peg. Source peg, auxiliary peg, and destination peg. There are n number of discs in the source peg arranged in ascending order of size. So here we see we have taken n equals to 3. That means there are 3 number of discs arranged in increasing order of size. So let this be disk 1, disk 2, disk 3, and the smallest one is at the top and the largest one is at the bottom. The problem is to move all the disks from source peg to the destination peg by using the auxiliary peg, but the constraint is only one disk can be moved at a time. So this is the Tower of Hanoi problem. Let us see how we can solve this by using the example of n equals to 3. First, let us see how we can do it for n equals to 1. So now n is equals to 1. So this is my source, this is my auxiliary, and this is my destination. So I am having only one disk. So if I am having only one disk, what I can do? So what I can do, I can directly move that to my destination. So this is source, this is auxiliary, this is destination, and I can directly move from the source to the destination. So if n is equals to 1, my step is from source to destination, and this is my goal, to move all the disks from source to the destination. So if we want to implement the Tower of Hanoi using recursion, my base case will be n equals to 1, where I can directly move from the S to D. So this will be my base case. Now let us see what happens for n equals to 2. That is when the number of disks is equals to 2. So this is my source peg, this is my auxiliary peg, this is my destination peg, and the disk. So this is my disk 1 and this is my disk 2. So I want to move all the pegs from S to D. Now what is my first step? So my first step. Now again the source, auxiliary, destination. I am having two options to move the disk D2 from S to A and from S to D. Now what we have to observe here is that if we move D2 to A, then we can move D1 to D in the next step. We always have to remember we have to reduce the number of steps for solving the puzzle. Now let us see if we move D2 to D, D2 to D first. So my D1 remains here and I can move D2 either to A or to D. So I suppose I move it to D. Now in the next step, that is second step, what I can do? So again I am having the three pegs. S, A and D, and now what is my objective is to move D1 to D first. So my D2 is here. So I need to move D1 here, or I can move D2 to here, because my objective is to move D1 to D first. So if I move S to D first, then what I can do, then there can be multiple combinations of the way you can do it. So at the next step, what I can do, I can move D2 to D auxiliary. So my D1 remains here. In the third step, I can move, this is S, this is A, this is D. So my pegs, I can move disk D1 to D, and D2 remains here. In the fourth step, so S, A, D, I can move D2 to. So the step which we did extra is this step. That is, I moved D2 to D in this step. So this is not necessary. If you see, ultimately what we are doing is we are moving D2 to A. So instead of moving to D, we will be moving it to A. So when that happens, so this particular step won't be there, and we can move D2 directly to A, and in that case, this becomes the first step, this becomes the second step, and this becomes the third step. So what we are observing is that if n is equals to 1, the number of steps required for solving the problem is, number of steps required to solve the problem is 1. So number of steps is equals to 1. If n is equals to 2, number of steps required is 3. Now let us see what happens if we are doing it for n equals to 3. And that is what in most of the cases you will be seeing, that you will be asked to solve a problem based on the number of disks is equals to 3. So let us see. So now n equals to 3. So our objective is to move the disk arranged in the descending order from S to D. So if this is the scenario, what is my first step? Now again, I have two options. I can either move D3 to A, or I can move D3 to D. But we should always focus on the problem that our intention is to move D1 to D first. So if we have to do that, how we can do it? So for that, our first step should be this. So at first we are moving D3 here. Again, a number of options. You can try different options, but you will be finding that the best thing about this is that when we are having n is equals to 3, whenever we are having n is equals to 3, so this is the arrangement of the disk in the descending order. Our objective is to move from all the disks in the same order from S to D. Now in the first step, you can have multiple options, like you can move D3 to A, or you can move D3 to D. But if you take any kind of combination, ultimately you will be seeing that this is what we are actually doing, like in case of the n equals to 2. So some of the steps, if you increase the steps, there will be some redundant steps which will be redundant in the sense that ultimately we have to follow the next step. So why not follow the next step at the first time? So our objective is to move first D1 to D, then D2 to D, and then D3 to D. So we will be moving towards that objective. So first we have put D3 to D. In the next step, D2 has been put to the auxiliary peg. In the next step, that is the third step, D3 has been put above the D2. So when it is done, you see the D, the destination peg becomes empty. So in the fourth step, we can move D1 to D. Once this is done, our next objective is to put D2 above D1. So how can we get D2? So if we move D3 from A to S. Once we did that, then D2 becomes alone in peg auxiliary. So we can move D2 to D1 in the sixth step. And then in the last step, we can put D3 to above D2. That is to the destination. So how many number of steps do we require? We require 7 number of steps. So if n is equals to 3, so if n is equals to 3, then we require 7 number of steps. And also, what is the sequence of movement? So the first movement is from S to A. That means one disc is moved from S to A. Here we are not mentioning whether the peg is D1, D2 or D3. Simply there is a movement of disc from S to A. Then there is a movement of disc from, sorry, the first step is S to D. The next step is from S to A. In the third step, there is a movement of disc from D to A. In the fourth step, there is a movement of disc from S to D. In the fifth step, there is a movement of disc from A to S. In the sixth step, there is a movement of disc from A to D. And at the last stage, there is a movement of disc from S to D. So we can see that S to D, S to D and S to D, these are the 3 S to D operations done for the 3 consecutive pegs. So the first one is for disc 1. So in the order, so this is for disc 1, this is for disc 2 and this is for disc 3. And in the middle, we are having a number of steps where the source and the destination are, sometimes the source is the source peg, sometimes the source peg is the destination peg, or sometimes the source peg is the auxiliary peg. Similarly, sometimes the destination peg is the destination peg itself, or sometimes it is auxiliary peg, or sometimes it is source peg. So now let us come to the formal algorithm for implementing the Tower of Hanoi in case of n number of discs. We are not concerned about the number of pegs because that is fixed. Source, auxiliary and destination. The number of pegs can only differ. So we have seen it for n equals to 1, n equals to 2, n equals to 3. Now we are going to see a general algorithm how we can implement it for n number of discs. So let us see that. So what is the algorithm for this? So we can write anything. We can write, see, this algorithm can be written in a multiple ways. So you can have multiple algorithms for this, but we are going to write this. So TOH, Tower of Hanoi, and I'm not writing the data type. You can write it to be char, you can write it to be anything. So n, so this will be definitely int n because n is in going to be an integer number only. So I'm simply writing in, and then what I'm writing is source for the source peg, AUX for the auxiliary peg, and DEST for the destination peg. So you can write anything. I'm again telling these are all part of the algorithm, so you can have anything. So I'm writing like this. And now the first thing is that we have to define the base case. Now what is the base case? If n is equals to 1, we have seen this. What we can write? So we can simply write printf, but because I'm writing a I'm writing a function in a pseudocode type, so I will not write printf. Rather, I will be writing move the disk from source to destination. Now here, remember, source to destination is my input, what is given. Else, if this is not the case, then what I have to do? I have to have 3 steps. What are the 3 steps? So first I will be calling TOH, that is recursively I will be TOH on n-1 source, destination, and auxiliary peg, that is the middle peg. TOH. Now here I can write TOH1 source auxiliary destination. I can write it like that, or I can also write one thing. I can directly write move from source to destination. I can also write it like that. So I can either write TOH1 source auxiliary destination, or I can also write move the disk from source to destination. And then what I can write next is TOH n-1 auxiliary source source and destination. Now, why the 2 recursive calls here? The 2 recursive calls are here needed because we are not only moving from the source to the destination using auxiliary peg, but we are also moving from, so this shape, so this particular shape is for moving from the source to the auxiliary destination, auxiliary using destination as the auxiliary peg. And then we are moving all the pegs from source to the destination using source as the auxiliary peg. So this is somewhat like this. So we have the source, we have the auxiliary, and we have the destination. So at first, we are moving all the disk from here, dot, 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 to here, and n-1 peg. So whatever n- pegs are there, all are moved from the source to the auxiliary. And what we will be left with after this is only 1 peg at the source, all the n-1 pegs at the auxiliary, dot, 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 and so that we can move this from the destination. So this is this step. And when we are done with this, so after this, when I am having my source, my auxiliary is having my n-1 number of pegs, and my destination is having this peg, the last peg. Now what I will doing, I will be taking all the peaks from the auxiliary to the destination using this as the auxiliary peak. So this is the concept in gist. We need to move all the n-1 elements at first from the source to the auxiliary using destination as the auxiliary peak. And then we have to move all the last peak, which is the last disk, which is at the source to the destination. After that, we have to move all the n-1 disk from the auxiliary peak to the destination using the source. So this is the concept. Now let us see the recursion tree for n equals to 3. So when we are having n equals to 3, what will be the recursion tree? So initially we are calling it for 3, that is number of disk is equals to 3. Source, let us call that A, auxiliary and destination. That means S, the source peak, auxiliary peak and the destination peak. So n is equals to 1, no. So where do it go? We call TOH. So when we call TOH, it is called on n-1 source, destination, auxiliary. So this step means the source remains the S peak, but the auxiliary peak now changes to the destination. The destination peak now changes to the auxiliary peak, and the auxiliary peak changes to the destination. So we write 2 S D A then now let us come to that part later. Now once it is done, SDA, now again it's a recursive call. So this part will be called again recursively, and when this will be called recursively, then it will become 1. Now the call is on source, auxiliary, destination. Now in this case, which is my auxiliary peak? Destination is my auxiliary peak. Which is my destination peak? Auxiliary is my destination peak. So accordingly, it will be changing like this. So the source remains the same. The destination is the auxiliary peak, so A, and the auxiliary is the destination peak, so it will be D. Now when this is done, n is equals to 1. So again a recursive call will be made here. So n will be equals to 1. So what is the step? Moves the disk from source to destination. So this will be transformed into S to D. And when this will be transformed into S to D, that means this will become my first step. So this is my first step. Next is, so once this recursive call is over, then this step will be called, so move the disk from source to D. So what is my source? S, and what is my destination? D. So it will be S to D. So this will be my second step. So my second step. In the middle, we have this part also, which I overlooked. So this part is over. Now when 2SDA, so 1 is there. So what is the next step from source to destination? So what is the source and what is the destination in this case? So in this case, the source and destination is S and A. So the movement will be from S to A. And so this will be my second step. Next, what is the recursive call? The recursive call will be on this part. So the recursive call is 1, and now aux SD, that is auxiliary source destination. Which is my auxiliary peak in this case? D. Which is my source? S. And what is the destination? A. So when this part will be recursively called, so it becomes n equals to 1, and then this transforms into the move the disk from source to destination. So the source is D and the destination is A. So it will be D to A. And this is going to be my third step. So this is going to be my third step. Once this is done, then this part is because this recursive call is over. So this is over. So what is the next one? Move the disk from source to destination. So we will go back here. So this is what the initial one. So what is source to destination? Source is S, destination is G. So we call, so this will be my fourth step. Once this is over, then the second recursive call will be made, and that will be on again 2, because n minus 1, so n is equals to 3 here. So n minus 1, that is 2. And now aux, source, destination. So what is my auxiliary peg here? A. My source is S and my destination is D. Again, a recursive call is made on this because it is not equals to 1. And I will just pull it down. Now first, it will be called on which part? First, this 1 will be called. So now 1. And what is the source peg here is A. What is the destination peg here? D. And what is the auxiliary peg? S. Next, again it will be recursively, so again it will be first this recursion. So first this recursion will be happening. So again it will be called, and now n is equals to 1. So move the disk from source to destination. So my source here is A and my destination is S. So this is going to be my fifth step. Once this is over, then again the recursive call will go back. We know that the recursive calls are made using the help of stack. So once this part recursion is over, it will go back to the initial part, that is the calling one. So this is the calling one. So when we go here, we are going to move the disk from source to destination. So what is my source here? My source is A, my destination is D. So this is going to be my sixth step. Once this is over, then the recursive call will be made on this part. And when it is made on this part, then, so again I am going to pull it down. So it will be made on n minus 1. So n minus 1 is 1. Aux is source here, S here. Source is A here. And destination is D. So n is equals to 1. So now the movement will be from the source to destination. So I move the peg from source to destination. So this is going to be my seventh step. So if we look at this nicely, what we can observe is that because these are recursive calls, so first with the call will be made on n equals to 3, and then first this part, that is the left one, will be over. So in which order? So first it will be 2SAD. So I will be marking it with small ABC. So first this will come, then this will come, then this one, then this. After that it will be this, and then it will be this. Once this part is over, then it will go back to this shape. Then it will be this, again this part, then this part, again it will go back to this, then this, and then this. That means you already know that, but just a repetition and a recap, that whenever a recursive call is made, first this recursion is totally over and it satisfies the base condition. Only then it moves to this shape. So first this recursion will be over, then it will move to this one, this statement, and then this recursion will be over. Now if we just write down the steps, what we have marked with 1, 2, 3, 4, 5, 6 and 7, we will be seeing the steps are like this. So first we are moving from source to D. Next, we are moving from S to A. Next, we are moving from the destination to the auxiliary. After that, we are moving from the source to the destination. Next, we are moving from the auxiliary to the source. Sixth, we are moving from the auxiliary to the destination. And at last, we are moving from the source to D. If you compare these steps with the one which we have got here, they are the same. So first from S to D, S to A. So S to D, S to A. D to A, S to D. D to A, S to D. Then A to S, A to D. A to S, A to D. And ultimately S to D. So this is corresponding to the one, the manual solving of the puzzle which we have done for n equals to t3, and our recursion tree is corresponding to that. So this is how you can do for n number of picks. Now if we have to find out the number of steps which will be required for n equals to n number of disks, let us try to find out for what we have already found out. So what will be the number of steps required for n equals to 3, that is n equals to 3 number of disks. So what we see is that A3, that is the number of steps required to solve a problem of size 3, is equals to, if we go back to the recursion tree, we find that there are two subproblems of size 2. So there are, to solve a problem of size 3, there are two subproblems of size 2 and a constant movement from the source to the destination. So we can represent that like this. So there are two subproblems of size 2 and a constant statement, which takes a constant time. Again, if we look at this problem, one problem of size 2, it involves two subproblems of size 1 and a constant time. So we can further write it like this. So A2 is two problems of size 1 plus 1 for the constant plus 1. Now, if we just look at A1, A1 means it's a problem of size 1, that means it's a constant time. So that means it will be 2. So the problem of size 1 means 1, because that's a constant movement, that is from the source to the destination, plus 1. So this is equals to into 3 plus 1 equals to 7. We have already seen that the number of steps which is required to solve a problem of size 3 in case of Tower of Hanoi is 7. So using the same logic, if we try to find out the number of steps required to solve a puzzle with n number of disks, we can write it like this: an equals to 2 an minus 1 plus 1. What is an minus 1? So when we are trying to solve a problem of size A3, we are basically converting it into two subproblems of size 2 plus a constant statement from movement from S to D. Similarly, when we are trying to solve a problem of size n, we are converting it to two subproblems of size n minus 1 plus this statement for movement from S to D. Now, again, like A2 can be broken up again into a smaller subproblem of size 1. Similarly, we can also break A n minus 1 into two problems of size n minus 2 plus 1 for the movement from source to the destination plus 1. That means it is 2 square A n minus 2 plus 2 plus 1. Similarly, if we go by this logic, then for solving a problem of size n minus 2, we need to break it down into a problem of size n minus 3. So it will be 2 cube a of n minus 3 plus 2 square plus 2 plus 1. So if we go by this way, by the method of induction, we can write 2 to the power n minus 1, that is when the problem size, so this 3 basically represents the number of times we are breaking it up. So if we are into the n minus 1 step, breaking it up, so we can write it like this, n minus 1 plus 2 to the power n minus 2 plus dot 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 plus 2 plus 1. 2 to the power n minus 1, a 1 because n minus n gets cancelled off, plus 2 to the power n minus 2 plus 2 plus 1. What is a1? We have already seen a1 is of size 1. So what is that problem? To move from source to destination. So a1 basically represents the movement of disk from source to destination. So that is 1. So 2 to the power n minus 1 into 1 plus 2 to the power n minus 2 plus 2 plus 1. If you just, because you can see it's a geometric progression, GP. So if you solve this, you will be getting 2 to the power n minus 1. So number of steps required to solve a Tower of Hanoi puzzle with n number of disks will be equals to 2 to the power n minus 1. You should remember this formula, but many times it comes that in terms of complexity, what will be the complexity of solving a Tower of Hanoi problem. Also, sometimes it comes in the term of how many number of steps will be required for some maybe given n equals to 8 or n equals to 50. So what will be the number of steps required to solve a problem? So you should remember this, and for that, you just understand the logic by which we are getting. So that ends the lecture on Tower of Hanoi.